Okay, welcome everybody to the weekly Bootstrap seminar. Today we are very glad to have Kamran Salehi Vaziri from EPFL telling us about Hamiltonian truncation in untitled space. And please start.
Thanks a lot for inviting me. It's a great pleasure to talk about our work for the Bootstrap community. Today, I'm going to talk about Hamiltonian truncation in ADS spacetime. It's a work that has been done in collaboration with Matthias, Marco, and Joao. This is the outline of my talk. I will start with the motivation and goals of our work, and then I will talk about a bit about the basics of quantum field theory in ADS and basics of Hamiltonian truncation. Then I will move on to the main problem, Hamiltonian truncation in ADS2, and talk about the divergences with phase and the prescription that we propose to get to extract observables, in particular spectrum. And then I will give you some examples of deformations of scalar field theory and conformal field theories. And then I conclude. Okay, I don't think I really need to motivate much this audience about quantum field theory in ADS. But anyhow, Hamiltonian truncation is a promising method to study strongly coupled field theories. We are interested in studying quantum field theories in curved background, the UV complete theories as relevant deformation of free or resolvable CFTs. In particular, the action would look like something like this, that the free or solvable CFT that we deform. We have a dimensionless coupling that we'll use a lot from now on. I call it lambda bar, which is related to the radius of ADS R and the coupling that comes up here. So we study in particular in two-dimensional ADS, which as a first step to study quantum field theory in ADS using Hamiltonian truncation, and it also gives us more examples to start with the solvable theories to start with. And it has some advantages. ADS itself is a maximally symmetric spacetime that has conformal symmetry that will give us this discrete spectrum that is very useful in Hamiltonian truncation. And also it has a conformal boundary that can help that or results connects to already well-established conformal bootstrap results. Yeah, that's it about the motivation. Let me quickly review some basic of quantum field theory in ADS and set the notations. So we study Euclidean ADS with the boundary at R minus pi over 2 and plus pi over 2 with this metric, you can see here. ADS2 has SO1, 2 symmetry, which has SL2R algebra, as you can see here with these commutation relations. And Hamiltonian here is the same as dilatation operator as the killing vector is in time direction. All Hilbert space will decompose as a consequence of that algebra I showed you into primary states I call psi and their descendants. So the action of Hamiltonian on these primary states is, as you can see here, gives the dimension of that state delta I, and the action of special conformal generator on primary vanishes it. And then we can also make our descendants by acting with momentum generator on these primary states. And also we have a unique vacuum state that I call it omega. Therefore, because of this setup, we have a spectrum that will look like some number of primaries with their descendants on top of them. So it's going to be a tower of one primary with the descendants on top of them. We also have, we can use the state operator correspondence to expand bulk operator as boundary scaling operators. In particular, if you have a state in bulk psi I, it corresponds to a boundary operator OI with dimension delta I. And then we can write down the bulk operator, this curly V, in any point in the bulk as we expand it as a sum over primaries I and the descendants and the distance from boundary, and with some coefficients, we call it BI, the OP of a bound to, boundary to bulk OP coefficients. In this study, we consider theories with no relevant deformation on the boundary, meaning that the delta, the dimension of boundary operators are bigger than 1, other than the identity operator corresponding to vacuum states. Just let me quickly review what we expect as like ADS of the phenomenology of ADS. So as I showed you in the beginning, there is this lambda bar, a dimensionless coupling that's in case that this power is positive, that we are considering that cases. With increasing lambda bar, we go from a small radius. So it corresponds, small radius corresponds to small coupling. And with increasing the coupling, we go to larger radius or flat space limits. So what we expect is that we have this bunch of multiplets, the primaries with the descendants which are integerly separated on top of them. For example, here each color represents one of these multiplets, and the solid line is the primary, and the dashed line is the descendants on top of them. And we start from perturbative regime, small r, small lambda bar, and we can do a perturbative calculation within diagrams. And then as we increase the coupling, we go to flat space limits. And we expect for the massive flows that we are studying, that in large coupling, we go to flat space limits. And the dimension, which will be within the dimension analysis, you can see that it's going to be mass times r, and as we go to large r, this happens, and then the slope of each of these lines will recover the mass of the flat space limits. Okay, this was some basic of what we expect. Let me just review quickly that what is the idea of Hamiltonian truncation and how it works. So Hamiltonian truncation is a numerical method we use that starts with the solvable theory. It can be a free theory or conformal field theory plus a deformation. As you can see here, H0 is is solvable theory, the free theory, or whatever theory that we know, the spectrum. And a spectrum is E, and we add a deformation. Then we introduce a UV cutoff, lambda, and we truncate our Hilbert space to finite dimensional. So we have this infinite dimensional Hilbert space. And with this procedure, that in particular, we say that let's get rid of all of the states that have energy bigger than this UV cutoff lambda. So we truncate our Hilbert space to finite dimensional, and then we can concretely build the Hamiltonian matrix, give it to a computer, and ask the computer to diagonalize it and read off the spectrum. And at the end, we expect, as we increase this UV cutoff lambda, we recover the exact value of the spectrum. So this is the whole ideology of Hamiltonian truncation. Let me just quickly give a very concrete example from quantum mechanics. That's a very simple example that you have a harmonic oscillator with a Hamiltonian, which is H0, as we all know, p squared plus x squared, plus a deformation. And here, specifically, I consider deformation of xn. And we truncate our Hilbert space based on perturbed theory spectrum. So we introduce some cutoff lambda, and we just take the truncated basis to the states that have energy smaller than lambda. For example, here I take the lambda to be 7 h bar omega, and I set h bar omega here to 1. And that means that you have the states that have mode 0, 1, 2, till 6. So you have 7 states. Your matrix will look like 7 by 7. This is the matrix, the Hamiltonian matrix. As you can see on the diagonal part, you have the unperturbed parts, which is half of h bar omega, 3 half of h bar omega, and so on. And we have the rest, which is this lambda that gives the part from the what is that? The interaction. So now sorry, I forgot to say that this is actually for n equal to 2. So I set n equal to 2, and it's just a trivial solution. It's just a redefinition of omega, omega. And we already know the answer of this. And as here, I just show you what happens. So we have, we set n equals to 2. We have this, the deformation of x squared. And we know the exact solution. It's a solid line. And these are the data of Hamiltonian truncation. And as you can see, when we increase or cut off lambda, it goes to the exact value. I set just h bar omega here to 1. And yeah. So these were the basics I want to just quickly discuss. If there is no question, is there any question so far? Okay, if there's no question, so let me go ahead and start the real problem. So when we do the Hamiltonian truncation in ADS, because of the non-compacted ADS, we see a divergences in all the spectrum, particular the vacuum energy. As we increase the UV cutoff, will become bigger and bigger and blow up. It actually linearly grows. As you can see here, the left line is, the left one is the phi squared deformation of a scalar field theory, and the right one is Liang, 2 examples. As you can see, by increasing lambda, the cutoff, the vacuum energy is growing, either in negative or positive, but it's growing. This is for some fixed lambda, small lambda bar. And the question is it a problem or not? I will discuss that in a moment, but let me just emphasize that this is it's the outcome of the non-compactness of ADS. As you can see here, if we introduce a regulator that cuts out the boundaries, the part that gives the volume, infinite volume to ADS, and then with that, here I'm showing a plot that we are just looking at second order perturbation theory coefficients. This phenomena happens to any order in perturbation theory. And for example, here for the second order perturbation theory, when we have the epsilon, the regulator, the vacuum energy doesn't diverge, and it just converges to some value. As we remove that, so here, for example, epsilon here for the orange is 1/5, for the green is 1/10. But as we remove that, it grows and go to infinity.
Does it matter for you that this regulator breaks the space-time symmetry, which you might?
Yeah, that's a very good question. It actually does, and then later in Hamiltonian truncation, we don't use this regulator, and but for proving about how it's working, we take in the limit of epsilon.
You're not going to actually use this specific regulators. It's just an example.
Yeah.
Okay.
So yes. So the question is that is it a problem that we have the vacuum energy that all of the energy spectrums individually are going to infinity? It's not a problem because vacuum energy is not observable, but gaps are. So what we're interested in is the difference of the excited state energy minus the vacuum. So one would expect that maybe with finding the difference of this energies, we find the observables, the gaps, by maybe some subtraction that happens that, okay, we have the matrix, we take a U, we cut off lambda, we find the matrix, we diagonalize it, we have the ith states, and we subtract it from the ground state of the same cutoff. If you do that, the answer would be finite, but it doesn't recover the correct value. In particular, it doesn't even converge. It's bounded, it doesn't grow, but it doesn't converge. So I'm just escaping how we find the prescription, but it's essentially coming from the studying perturbative description, perturbative method, and we got this prescription that works, and I will talk about how it works later. But for the moment, the prescription is the following: that we have the state, energy of the states of epsilon EI that we want to find, and to do so, we take the Hamiltonian in a shifted cutoff, lambda plus EI, and here EI is the unperturbed energy of state I, and we subtract from lambda. So there's a shifted cutoff in this subtraction method. And as we take the cutoff, UV cutoff lambda to infinity, we recover the correct values. So I will show you later the examples, the trivial example that we know already, the solutions, and we check this prescription and also some new results. But before,
but can you comment on this prescription? Because why are you allowed to use perturbative data in formulating the prescription? So I'm a bit worried about the fact that EI appears in this equation, a small EI.
that's true. That in fact, when we are, this is a problem maybe with this prescription. As for example, sometimes when you go to high coupling, there are some crossing happening, right? And when this crossing happening, you should actually go back and see where these states are coming from to subtract. This is true, but at the same time, this prescription recover the correct values, and we check that with the Hamiltonian truncation. Putting
why do you call it a prescription? Can't you just derive it from some principle? Why do we have to guess? We are just diagonalizing some big matrix. Can't you just like understand what's going on? And
okay, I have maybe a nicer motivation at how we found it. Maybe at the end I show you if we have time. It shows how actually we came up with this. Maybe that helps.
Okay, let's see how it works.
Well, just one more question. And this prescription works whatever the divergence structure of the QFT? I mean, are you assuming here that for this prescription to work, the energy would be finite, like in a flat space context, like the cosmological constant is finite? Or I mean, you would use the same prescription if there, for example, if the ground state energy was actually divergent?
So this prescription works when it's finite, right? Because when we take lambda to infinity, the difference is like
right.
is.
So it's for those specific kind of theories that this is the right prescription.
No, this is the right prescription for the for both the theories. So for the case of ADS that they are going to infinity, this is the right one. This is the only one to gives this particular shift is giving the right spectrum. But for the flat, for example, on the cylinder, if you change it with 2 EI, 3 EI, or 4 EI, it still gives the right answer as you go to lambda to infinity, because the difference will go to 0 anyways. But because they're not growing, right? Individuals there, all of the spectrum will look like this anyways. So it doesn't matter if I cut from here or here, the difference is going to 0.
But that's because your vacuum energy is in the flat space limit is finite. Does not depend on lambda.
No, not for our prescription here. It's actually, yeah, it's not given that. No, we don't care about that. It's okay if it's in flat space limits is also growing. It's actually in all of our cases it's happening. Yeah. No, it's all in both. Yeah.
I'm not sure. I think there is a bit of a confusion. I think what Am is trying to ask is if there is some extra divergence coming from the bulk, which is not associated with ADS, right? So indeed, this one we are regulating the divergence that comes from ADS, right? Not just yeah. We are focusing on that. Yeah.
Okay, this is the prescription. Let me just give you the sketch of the argument that how we, under some reasonable assumption, we prove it. So the idea is that we introduce the regulator epsilon, and we have the integrals of deformation V of convergent finite. And then we use the perturbation theory first at second order, and then we generalize it to all orders. As you can see here, this is the perturbation theory, the notation I'm using, that it's the EI, the small e is the unperturbed spectrum, and then we change it with lambda bar, and this CIN is the coefficients of this perturbation theory. And then we introduce this rho, this spectral density, and or coefficient of perturbation theory coefficients will be integrals over this spectral density. And this is actually the quantum mechanic perturbation theory in a compact form that we introduce. And this spectral density are related to connected correlations of insertion of this potential V, the interaction at different points. And it's just a Laplace transformation of this spectral density gives the connected correlations. By connected correlation, it means that we subtract the parts that the insertion of the same state I is inside. So these three formulas are actually quantum mechanics, the Riley-Schrödinger quantum mechanics we know in textbooks of quantum mechanics. It's very compact and has all the orders here. While if you just open Wikipedia, you can see that they call it the compact notation, as we all had in our textbooks. It gets bigger and bigger in higher orders. So in particular, we are very proud of this compact form of quantum mechanics perturbation theory that we introduced. And okay, let me go back to the main problem. So we were subtracting two different energies. So in particular, I will rewrite those formulas now in terms of the vacuum perturbative coefficient at nth order, and the one that we want to look at, the excited state. And it can be written as an integral from 0 to some cutoff, the UV cutoff that I introduced, over this delta rho, that is the difference of those two spectral density. And what we want to see is that this delta rho it would be bounded to find that this is actually convergent. And this, for that reason, we look at the large alpha. And then this delta rho is actually Laplace transformation of this function g, which is the difference of the two endpoint correlation function of v. And we introduce this epsilon to make all of this integral here convergence already. And then we later take epsilon to 0 limits. So in particular, each part of this G looks like this. It's removed, strip is removed by epsilon, and then we have insertions. And important thing is that as we go to alpha to infinity, it translates that all of this T goes on top of each other. And since we set one of them to 0, it means that all of them all simultaneously goes to 0. And so that means the relevant singularities in G will come from the simultaneous collisions of multiple operators on a unique point on the boundary. Since we are taking epsilon to 0, the important part are coming from when they meet at the boundary. And at the same time, they go into the same T. All the T goes to the same point. The way I forgot to say that this vector notation here means like tau 1, tau 2, tau 3. And also here, this is just schematic of d alpha 1 over alpha 1 minus EI, all of them, the product that I had here, just to remind you the notation. And then later we can use that boundary OPE to expand this collision and study this collision of the multiple operator, bulk operator going to boundary. And as a byproduct, we can also find the convergence rate of Hamiltonian truncation, which is sensitive to the first operator that appears in boundary OPE. And we call that the dimension of that operator delta star. And the convergence rate is actually 1 over, or some proportional to 1 over lambda delta star minus 1. And we will see later that it actually shows up in different places. Okay, that was the sketch of the arguments. I will go now to more concrete examples to actually, yeah, this was a bit abstract and too technical maybe, but now there will be some concrete examples. But any questions so far? Okay, if not, let me just.
Can I ask?
Sure.
I thought, I'm not sure. So is this a region where the boundary OPE converges? If I take a stack of operators extending an ADS and I squash them all into the boundary, is there a boundary OPE channel that converges there?
Right. We assume that this is happening. This is related to the this part that we expect that the deformations are right, has this delta bigger than 1. Yeah, we assume.
I guess.
Yeah.
Can I make a comment?
Maybe I'm not sure that I understand the consequences of the question I'm asking, because you said you made a comment about the boundary OPE, but what is it important for? It is just in the previous slides you said something. What did you say? You said the convergence rate is.
Well, maybe that. Yeah. So. I don't remember the details we use, but we have the assumption that they actually converge, and in the examples that we have, we show that this happens. So I'm not.
Maybe I can just clarify. Sure. So could you go to the picture of the OP? Because I think I can. So what you're saying is that if I just try to take one operator at a time at the boundary and use that OP, that is dubious, and I perfectly agree with you. That's not the OP that is used here. Here, the OP that converges, as you see from the dashed line, is the one in which you replace all of those things with a state. So with a unique operator. So then the thing is, this is a convergent OP whose coefficients are functions of cross ratios. So we cannot fix the OP completely, but the overall power, the rescaling, the overall power that comes from rescaling all the operators, that's what's gonna what is responsible for the singular, for the scaling of the convergence of the, like this formula, the last formula in the slides, the scaling with lambda, etc. So the actual coefficient Ci will know about some integral over a complicated function, a higher like a higher point function ADS, but the power depends only on the total rescaling.
Yeah, in particular, like I mentioned it here, but I forgot to emphasize that we find that there is the uniform band, that there is the epsilon independence in that coefficient that's coming from, and it's epsilon independent. So as we take epsilon to 0, that's still fine. Yeah.
Okay, thanks.
Okay, so let me go ahead to the examples. So first we take the deformation of scalar field theory. In particular, we study phi squared and phi for deformations, as you can see here with lambda 2 and lambda 4. And we start from the free massive scalar. And before studying phi 4, let me just set lambda 4 equal to 0 and study this simple test of prescription, as we know that just phi squared term is just the redefinition of a free massive theory. Here, the delta I'm using is coming from this, is related to mass, bare mass, with this relation, delta times delta minus 1 m squared r squared. And then as we deform phi squared with lambda 2, we redefine the mass. And we can, the spectrum again will be the same. It would be some one particle state, two particle state, three particle state. Each have the delta, like one delta, two delta, and the towers of descendants on top of them. So that's what our spectrum will look like now with the redefined delta that is coming from this relation here. And just lambda bar here is lambda times r squared. So what we will see when we do the Hamiltonian truncation, here I'm showing how the convergence is happening. So for a fixed lambda bar, some coupling, I'm showing the first excited energy minus the ground state energy, and I'm increasing lambda, the cutoff, UV cutoff. And as I increase, they go closer and closer to the exact value, which is the solid line here. And it actually matches with the fit that we expect, which is it should be 1 over lambda to delta star minus 1. And here this delta star is 2 delta, the first boundary operator that shows up. And yeah, so it goes to exact value as we expected with this prescription. And on the right one is the same plot with now 2 particle state, that here for this particle delta that I'm showing becomes the third excited state. We also want to recover SL2R, as we discussed that this SL2R will be broken by introducing this UV cutoff lambda, and we want to check if SL2R is recovering. And here I'm showing on the left, both of them, but on the left one first, I'm showing the low coupling lambda bar equal 0.1, and I'm showing first excited energy effects descendants minus the primary. And it should go to 1. It should be integerly separated, right? And then, as you can see, with increasing the UV cutoff lambda, it's going nicely to 1. For higher coupling, it also happens, but the convergence is a bit slower. It's still, even for lambda bar equal to 2, which is far from perturbative regime, it's still recovering it up to like 1% error. Here is the spectrum. So what we actually see is that so there are 1 particle states. First one here for the particular delta that I'm showing is 1.62. So it's 1.62, 2.62, 3.62, the descendants on top. And for example, the blue one is 2 particle state, and it's descendant. And the points are the Hamiltonian truncation data. And yeah, the dashed lines are perturbative calculations. As you can see, will go off right after 0.6, 0.7, which is the radius of convergence of perturbation theory in this particle delta here. And they're far off. The red one is the second order perturbation theory. The green one is third order perturbation theory. They will be off at this point, but Hamiltonian truncation with the errors are still very close to exact value. So, and here R bar is defined here. It's just a dimensionless coupling that is proportional to radius of ADS. So that shows that this is the test of the prescription. If you use another, for example, naive prescription, they will be off. And the convergence will not even converge here. So that was the test. Now we take the 5-4 deformation. Just before going to the details of ADS, let me remind you.
You showed some formulas which, for your convergence plot, where
Mhm.
if you had delta less than 1/2, I think, where you have modified boundary conditions, it looked like it would predict it doesn't converge. Is that right?
That's true. Yeah. So that's a.
Can you do? I mean, do you just need to do something different in that case, or is that still a puzzle of what you would do?
So that's a very good question. I will come back to that at the end because it's related to some other speculation we have. I will come back to that later. But yeah, we didn't consider that. We didn't study the one that are below the BF bound. I will talk about it.
But you could, I mean, you can have a situation where the perturbation lowers the delta, right? For example, if you have a critical point.
Yeah. Yeah. Sure. I will show that some some plots about that. Yeah. So so for a phi for deformation, what happens in flat space limit is that in flat space is that we know that the Z2 symmetry will break at some coupling when you increase the coupling, and a phase transition happens. And in particular, that phase transition happens in some critical coupling around 3. So, and what you see there is that the first excited energy gap will close, and the first excited energy minus ground state energy becomes 0. The question is that will we see this spontaneous symmetry breaking in ADS? Because at the same time, ADS is an infinite space volume, but at the same time, it looks like a box because of discrete spectrum. The question is that, does that happen? So we argue that using semi-classical calculation, that if you take a Landau-Ginzburg theory and you study the minimum of the action by considering a bubble of a true vacuum inside the false vacuum, what happens? And we conclude that we have the 2 cases. One is that the minimum of the global minimum is just 0 and phi is 0 everywhere. Or if we have a bubble of phi t and we increase the volume of this bubble and this bubble becomes bigger, the action decrease, and that means that this bubble wants to become bigger all the way to boundary. So then we also see that the spontaneous symmetry breaking happens in ADS as either you have all phi equal to phi t or phi equal to 0. And then this is the result of Hamiltonian truncation when you have phi for deformation. So on the left part, I'm on the y-axis.
Can I ask something basic? I think I'm missing some basic point. Where do we see the ambiguities when we put a theory in ADS that there are many curvatures we could add and so on?
Many curvatures of?
So if I have a theory in flat space, the way to put it in ADS, I guess, is not unique, right? I can add many ways, even for a free scalar, right? It can be minimally coupled. I mean,
right. So you can.
So there is a family of theories when I put in ADS, right? It's not unique. So
right, you can take that and you can redefine the mass. So we are taking the normal order action with assuming that minimally coupled are already absorbed to the mass, and we start with some redefined mass in the beginning. That's what's happening.
But is that the only ambiguity you have? I mean, if you have many terms, it's not just a free scalar. Don't you have many more ambiguities? Maybe not.
I don't think so. Yeah, because it's to the 2-dimension. You just when you normal order, you have some tadpole divergences, and you can with normal order, you just get rid of that, and it gives the phi squared term to the action, and that's it. There's no ambiguity, I guess.
Okay.
Yeah. So on the y-axis, I'm showing the first excited energy minus a vacuum energy divided by some delta to make it all start from 1. And I'm increasing on x-axis the lambda bar, the coupling, and the gap will close at some point. This is the critical point that the Z2 will break. And this for each delta, you can find the critical coupling, and it itself, it's a new results. And one thing that we will like looking after to see if we are recovering flat space limit is that as we increase delta, and delta was when you go to large coupling or large radius, because equal to MR, so large radius is equivalent to large delta. As we increase delta, do we recover the flat space limit? And up to errors, we actually do. So for example, here, as I showed you, the critical coupling was around 3, it's actually 2.97, I guess. Here we go to 3.2 for delta equal to 9.72. This is the highest delta we could go. And up to the errors, we are actually matching with the flat space limit results there. So yeah, so that was the part from scalar field theory. If there's no question, yeah.
Maybe,
Yeah, I actually
maybe
have
I
a
can
question
ask.
about this. Yeah. Okay, Balt, go ahead. Yeah, let's go.
If you have a double well potential in ADS, I thought there were some claims that the phi equals 0 point was stable because your mass may be negative, your mass squared may be negative, but you're still above the BF bound.
Yeah, that's true. So that's a very, very good point. So I skip this kind of details. And that's a important point that actually gives the hint that maybe in ADS, we can see this continuous symmetry phase transition, say the first order phase transition, as you can stay in that stable part and then suddenly jump to the broken phase, Z2 broken phase. That's true, actually, yeah. So we comment on that in our paper.
I see. Okay, thanks.
So,
Yeah, so my question, I also had a question. So of course, in that old work with Lorenzo Vitale, we also had a box, right? We had to do a computation on some interval of length L, and we would then try to take to infinity and so on. And so here you have a different kind of box.
right.
And you are saying that if you try to take it large, then somehow in your box is harder to make it large than the box that you had with Lorenzo. So is there any intuition why your box is difficult to make large?
I'm not sure if this statement is actually like complete, because you are using that renormalization procedure there that make the convergence much faster, right? We didn't use that. This is just normal.
It's like raw, like
yeah, raw, exactly the raw one. So I'm not sure if we implement that happens, but that's a very good question. Yeah, I don't know.
Maybe can I add one thing here, because I think one reason why we could expect something harder here when we're harder, I mean, like there's one more ingredient, because when you renormalize like the non-analyticities that you're taking care of will come both from the bulk, so local divergence, I mean, they're not divergence, but local non-analyticities, say in a correlation function, small tau in the bulk, like in flat space, this is completely analogous. But then there are also non-analyticities that come from the boundary. So you will have all the same, you can never beat here the convergence rate of flat space. And you have, in addition, a boundary. So it's a little more like trying to take larger strip rather than the cylinder. So there is some reason why, at least in Hamiltonian truncation, it's not easy to do better here than in flat space, because there is one more thing in the game.
Okay, thanks, Marco.
Okay, I think I'm doing terrible in time. Okay, let me go ahead for the other part of the examples, deformation and conformal field theories. So I just quickly review some basics of conformal field theory in 2D and boundary CFDs. So conformal field theory in 2D has the Virasoro algebra, and we in particular are interested in minimal models. We start from minimal models and deform them. Minimal models are the theories with finite number of Riemann module. An important fact is that ADS is conformally flat, as you can see here in this metric, the Poincare metric, that up to this Y factor, the metric is flat. You have this boundary is equal to 0. And then if you put a CFT in the ADS, it's equivalent to a CFT in presence of a flat boundary. So then if you have a CFT in ADS with some isometry preserving boundary condition, it will be related to a boundary CFT with some Y transformation. And in particular, all the commutation relations will be similar to the one that of the flat space up to some Y factors. So I just list some facts about boundary conformal field theory, that there are boundary conditions that we take, the consistent boundary conditions, and then the number of these boundary conditions are equal to the number of Virasoro primary operators. And in particular, there exists always the identity boundary condition that breaks all the symmetries and exists in all the minimal models that corresponds to the identity module. And we are interested in this boundary condition. So the data I will show you is just from this identity boundary condition, although we will comment, if I have time, at the end about the other boundary conditions. And the first operator that shows up the boundary is L-2, the displacement operator, and its dimension is delta star equal to 2. That gives us the convergence rate, the universal convergence rate for all of this deformation in conformal field theories. As I told you, that the convergence is 1 over lambda to delta star minus 1, and here delta star is equal to 2, so the convergence is always 1 over lambda. So let me give you the first example, that this example is also, again, exactly solvable. So this is a test of our procedure now in conformal field theory deformations. So we take Ising model, which has this information. The central chart is 1/2. It has 3 modules, 1, sigma, and epsilon. And we take the thermal deformation that looks like this, adding this part to the action. We add epsilon to the action, and the solution is the exactly solvable theory. It corresponds to the free Majorana fermion with the mass 2 pi lambda, and the spectrum will be consist of 2n particles, 2 even number of fermions. In particular, the energies will look like this formula. So this part is coming from the kinetic part, that each fermion has 1/2 energy plus the mode that they go into, and the mode should not match because of the Pauli principle. And this part is from the interaction term, that instead of lambda, now I'm just inputting the mass of the Majorana fermion. And as I increase the radius, the energy should grow linearly. And here I'm showing the first excited energy minus the ground state energy. And the blue line is the exact value, is exactly this formula for Ni equal to 0 and Ai equal to 1. So it starts from 1/2 plus 3/2, which is equal to 2. And it grows as I increase the radius, and it linearly grows. And as you can see, the data from Hamiltonian truncation is converging to exact value. And in particular, here I'm increasing them. And in particular, the green points here are the extrapolation that we use that convergence 1 over lambda to extrapolate this. And it matches with, first of all, with that convergence rate. And this is the extrapolation point. And as you can see, it matches surprisingly very good to the exact value. Just note that we are really here in really strongly coupled regime, because we started from 2, we are already in 25, and the difference is pretty small. So this is, again, another test of this prescription. So now I show you here the Ising model.
Can I ask a question about the previous plot? So here I don't see. So I see that you are approaching the exact result from below, right?
Yes.
So there is no for this particular observable. There is no. I guess it's not so surprising. So there's no actual monotonicity because you are because these are energy levels. It's not the ground state.
Yeah.
Sorry, it was an obvious question. Sorry.
Okay, so here I'm showing now a non-trivial theory that we studied. It's the Ising model with a magnetic deformation. So here, instead of this epsilon, we have sigma deformation. And so I'm showing a spectrum here. Forget about the colors, it's just Z2 parity, even odd sectors. And we have the first primary, as you can see, and the descendants that are integerally separated, and then second primary that corresponds to 2 particle state, the beginning. And So this spectrum itself in this region is a new results from the Hamiltonian truncation in ADS. But we were also a bit ambitious with what happens in flat space limit. Do we recover the flat space limit? And by the way, after this R bar equal to 1, the convergence becomes really poor. So we cannot really trust the Hamiltonian truncation. But this plot itself, we can trust. And so the flat space limit is an integrable theory with 8 particles, 3 of them below the 2-particle spectrum continuum, sorry. And the mass of this second gap and first gap, the ratio is approximately 1.62. So we were curious that if we recover this flat space limit. So when you look at as I showed you in that ADS phenomenology part, the slope will correspond to the mass of the flat space. And so we look at the ratio of the second slope here and here at this R bar equal around 1. And it recovers 1 to 1.5. So we are not completely recovering the flat space limit where we were closing, but maybe if somebody does a better numerics, it can recover a bit more digit flat space limit. Okay, I think I don't have time to discuss Lie deformation.
Why do you need to do this slope? Why can't you just take the ratio? The factors of R, you can't get to large enough R. The factors of R would cancel out. Right?
The ratio.
You're just looking at the
ratio of the energies, you mean?
Get the ratio of the energies, yeah.
But already here we're starting from 2 and 4, and this is the most we can actually trust. And we can go to 1 that we can actually trust. And the difference of here is 8 and 4, and the starting point is 4. It's not like that we already in very high energy and we can neglect this 4 and 2. So we look at the slope. That's a good question, but I think we considered the other one, but we're convinced that this is a better measure, that we look at the slopes, because we are not in a very high energy already. And
I see. It's because you have a constant shift. So if you do this in TCSA, you can with a fairly small number of states, you can just take the ratio at large R and you get 1.62 pretty good accuracy. But you're saying here, because of ADS, you have a shift, which forces you to the slope instead.
Oh, the shift, by shift, I just meant the starting point too. So
yeah.
I mean, but there also, you have it, right? So you just, but you can go with pretty large coupling, that it's much larger than this 2 or 4. And for us, we couldn't go that far because the error becomes pretty big. So
yeah. So for some reason here, you're not able to go to large enough R where you see the.
Yeah, I mean, the reason is that the Hamiltonian truncation is not convergent. I mean, the errors are big. That's the reason, yeah.
And for some reason, because of the issues with the ADS curvature and the errors are larger than they would be if you just did it.
Yeah. So by ADS, if you meant that, yeah, exactly. That's coming from there. That's true. Okay, so I skipped the Liang part. I just, how much time do I have? Is it 5 minutes or? Maybe, yeah, I skipped Liang. I just talk about the speculation we have about the negative lambda bars. So what we did is that, okay, we investigate lambda bars that goes positive, and we were thinking that, okay, what happens if we go to lambda bar negative? So this is a plot, for example, of Liang, that when you start from lambda bar 0 and you go to negative bar, it has a good convergence up to some critical point that the Hamiltonian truncation becomes severely poor. And as you can see, the convergence here, maybe it's better that I zoom in. It's very good here. They're all on top of each other because it's a very fast convergence. But here it becomes very poor when the gap is around 1, that at some critical coupling lambda bar, that the corresponding energy, first excited energy minus grounded state energy becomes 1. So we were we also saw that in Ising magnetic deformation. So here I'm showing the Ising magnetic deformation plot without the errors. I show you that why the errors are big, but here is the point that the errors become really big. I don't show the errors, but I tell you, I will show you later. Yes, so here I'm showing that why the errors are big. So for example, the left plot is for lambda bar, not very big, correspond to this point, around this point. And you can see that SL2R is recovering super good. As you can see, the difference of first descendants and primary is almost like exactly 1 with a very small error, and it's converging to 1. But then if you go around this point, as I'm showing you, the SL2R is not recovering. First of all, the difference is much bigger from 1, and the deviation from 1 is much bigger. It's not converging to 1. It's Hamiltonian truncation doesn't converge. And we were curious at what's happening there. And we were saying that, okay, let's go to the exactly solvable theories that we know. And then in exactly solvable theory, what happened is that, for example, on the right plot, I have thermal deformation of Ising. And if you start from a boundary condition of identity boundary condition, this was the part that I showed you, the line. And if you go to negative, you will go and you meet the other deformation from the other boundary condition. So you have the other boundary condition sigma to start from 1/2. And if that goes also to negative, they meet at some lambda bar minimum equal to 1. Same thing happens for phi squared deformation, that we start from Dirichlet. This is the part I showed you. And if you go to negative, it will meet the other leg that is coming from the other boundary condition, the Neumann boundary condition, at some critical lambda bar minimum that corresponds to the delta equal to D, now D equals to 1. Then we gave this ambitious speculation that all conformally invariant boundary conditions for a given CFD is connected by relevant deformation of this CFD in ADS. So in particular, you start from some boundary condition, identity boundary condition, and you go to negative, and it connects with the other boundary condition, sigma, that flows, is deformed in ADS. And when you go to negative lambda bar, they meet each other at some point here. So they're connected in that sense. And this is also what we expect.
And what happens when you say they're connected? So what the theory which is happens at the intersection? What is this theory?
So this is the very good question. So what we expect is that this is the part that the marginal operator at a boundary appears. So this is a delta equal to 1, and so we think that there we cannot. It's like the dangerously relevant operator that shows up if you go to that region, and you cannot fine tune them. So that's the reason that this point is yeah, that thing happens. So what we expect is that the boundary operators that are living there will not be at this point. There are going to be some marginal operators that happen. So that's what we expect. And
do you have time to comment why these two pictures look different? In one case you have annihilation, in the other case you have kind of going through.
This is also a good question. So the other one here, so the sigma boundary condition. So yeah, so for the other ones, we also expect that this thing happens, that this annihilation happens. But for the Ising one, we expect that since sigma, so one is the Z2 preserving, but sigma is the Z2. Sorry, the other way around. Identity is Z2 breaking, but sigma is Z2 preserving. So it can't, yeah, actually pass at this point. I will come back to this maybe at the end. I have, I have.
Okay, thank you.
Do you have some more motivation for this conjecture that you put on the previous slide? I mean, you draw two lines in a plane. They meet, fine. But do you say that all such lines in higher dimension, like why should I believe this conjecture? Is it obvious that this is true, or I just don't see where the conjecture comes from, given what you said, like the full general conjecture.
Yeah, it's just right. This is a speculation, and we are not. This is the evidence we have. So the evidence is that there's something happening for the Hamiltonian truncation for Liang or magnetic deformation, that they don't converge properly at this point. So we were thinking that maybe something is happening, and this, like, some ambitious speculation is that these are the evidence we have. So yeah, you can maybe it's a bit too general and yeah, statement in red, yeah, but yeah. So this is also what happens, we expect happens. So this is schematic plots. So this part leg of the plots we already studied. I didn't show you, I passed. And also this part of the plot for magnetic deformation. And we expect that there should be another leg that comes from the other part, and they meet at some lambda bar minimum. So that's our picture with speculation. Okay, let me just.
Did you maybe consider, at least if the counting of the number of relevant deformations and number of boundary conditions, is consistent in known models? For instance, your conjecture would say if you have a 2D CFT with no relevant or marginal operators, then that immediately predicts there's only one conformal boundary condition. Is that always true? I mean, I don't know.
So I didn't get your question. Can you repeat? Sorry.
Well, you have a conjecture, right. And maybe you can't check it exactly, but it seems like it implies some interesting consistency conditions on sort of the number of different conformal boundary conditions and the number of relevant operators. And I'm just wondering if you checked that in known examples. So for instance, if you have a theory with no relevant operators in 2D, then that your conjecture would imply there's only one possible conformal boundary condition. Right, because if there were two but no relevant deformations, you can't possibly go between them because there's no.
That's a good question. I don't know. No, we didn't consider. Maybe Marco can comment about this. But I think that.
Yeah, we did not think much about this. I think it's a good point. Do we know? Because the point is that minimal models will have these operators, and it's hard to find boundary conditions known exactly for like, I don't know, also, but I guess WZW models, they will have a current, but that's not a scalar. I mean, I'm just saying, it's not that there's a lot known about the boundary conditions for 2D models, right? We know the classification for minimal models, and we know some boundary conditions which are preserve the current for WZW models. So I don't know if in any of these cases, probably in the WZW models, there are, like, this is something trivial, I don't know, like, are there models which are under control, like WZW models that don't have a relevant information? Or not?
Yeah, you can do orbifolds to get rid of all of the relevant deformations.
Right. So in that case, yeah, that's a good point. In that case, we could look at the set of, because since these are orbifolds of models with a global symmetry.
Yeah.
So then at least the symmetry preserving boundary conditions are known. Yeah, thanks. I don't know if Joao thought more about this, but it's a good point.
No, I mean, our goal was this. We didn't even call it a conjecture. Our goal was to motivate you to prove it wrong with this example. So we thank you very much. We will think about this suggestion.
Yeah. I over-advertised or speculation probably. Okay, let me just conclude my talk. So in summary, we use a Hamiltonian truncation to compute the energy spectrum of QFT and ES. So as I showed you, there are the problem with these divergences because of the non-compact nature of ADS. So we propose a prescription to find the observables, the spectrum, and we derive the compact form of quantum mechanics along the way of perturbation theory at arbitrary order. And we speculate that that all the conformal boundary condition for a given theory are connected by a bulk renormalization group flow in ADS. And this is just a list of possible future directions that we can go to higher precision. We can go to higher, if we implement a method to have higher precision, then we can go more to large value of R and investigate large flat space limits. Another thing is like the proof or disproof of the speculation that we just talked about. Another thing can be we use a SL2R rather than just checking it. So we were checking it here that is it's recovered or not. But we could implement that it manifestly is either SL2R, and then we construct or Hamiltonian truncation based on the for example, the states that are primary and descendants are annihilated by K. And also studying other observable like S matrix, and also a more rigorous proof of the procedures I just talked about, because we have some assumptions there that maybe it's not as rigorous as possible. So it's better that yeah, we think about that. And also like higher dimensions. Yeah, that's it. Thank you so much.
Any other questions?
I wanted to ask what do you mean by using SL2R? Do you have any concrete suggestions how this could be done?
Not, to be honest, not, but maybe Matthias, if it's here, maybe you have some comments, but we don't have much concrete. It's just the idea that maybe we do this. I had some calculations about this, but it's really a bit technical, so we didn't implement it already, but maybe. This calculation I did 2 years ago. I forgot the details right now, but yeah. But right now we don't have a concrete proposal for that.
Yeah, maybe I can add. So I agree with Kamran. We tried some, but we never got to an algorithm that we could use SL2R exactly. But perhaps something simple, which I'm not even sure if it's more efficient, we haven't tried it, that we could use K, which is also a generator, and try to look in the subspace of the kernel of K, the special conformal generator, and only diagonalize there. We'll only look at primaries, but maybe it's as hard as diagonalize the full Hamiltonian because, well, K is also a complicated generator, so we did not really play with that.
I also want, I don't know how you guys, when I started thinking about this Hamiltonian truncation, and indeed in the literature, before we started working on this, Balt, Matthijs, Lorenzo, there was indeed in the literature some proposals. There were some proposals about this level-dependent truncation, the level-dependent subtractions they were calling them. So people like Watts were advocating them and so on. So when I looked at them at the time, it just didn't make for me absolutely no sense, because I thought I was reluctant at the time to consider proposals which do not allow me to just like pick a fixed value of lambda and do everything for this fixed value of lambda. I didn't want to consider proposals which required like going in little steps, increasing lambda, so that you know exactly where every state is coming from. So I completely didn't like it, and in fact, we completely managed to renormalize our theory without this state-dependent subtraction. Now you are coming back with the state-dependent subtraction, but maybe, I don't know, do you have any discussion in the paper where I can look to get myself more comfortable with it? Did you internalize it somehow that you think it actually makes sense?
Slava, maybe this slide help you. So this is why the motivation that why we got that thing. So here I'm showing just 5 squared deformation. So take a 5 squared deformation as some ladder operator, and then the potential will look like this if you normal order it. And then let's look at the second order perturbation theory contribution.
No, but I know if you do perturbation theory, yeah, that's how everybody justified it. But this just doesn't make any sense non-perturbatively. Because I non-perturbatively, I should just pick a value of lambda and be able to do a computation at lambda. And nobody tells me where every state came from. How do I know? I just get a list of eigenvalues. How do I know that my eigenvalue came from that non-renormalized free state or from this? It just doesn't make any sense.
But maybe, can I ask maybe a practical question? I mean, okay, let's say we go with this procedure. Since you're diagonalizing different matrices for different states, I mean, do you have some estimate of the error since they're not actually orthogonal? For example, eigenstates aren't technically orthogonal mechanically, right? So, you know, when you are going to start computing, I don't know, correlation functions and things like this, I mean, do you have a sense of what the error is going to be? Because it's not a single matrix anymore.
Right. So example by example, we found that what is it? It depends on the so there's a convergence rate that I show you. So that's one thing that you can it shows the like how much error you expect.
That's the energies. I'm kind of more asking, do you have some sense of the error in the wave functions? If you were to compute, you know, a correlation function or something like that, right? And now the vacuum is not exactly the same Hilbert space as the excited states or something like this.
No, no, to be honest, no, we don't know what's happened. Yeah. That's a very good question. Yeah.
I see. You mean just because lambda is different when we do the subtraction? Yes, yes.
Right. I mean, it's conceivable that the error is under control, but it needs to be, you know, sort of understood.
Yeah, so one thing to sort of keep the discussion from Slava's point of view, it's not, I mean, one thing you could do to try and be systematic would be to use some other regulator so that now your theory is finite and then start integrating out. Because if you just start, one problem we had in trying to think in terms of lowering the cutoff is that the theory with infinite cutoff just does not exist. It's not a Hamiltonian with finite energy levels. And so since you want to sort of recover the right continuum limit, but you don't have it at the level of the Hamiltonian, you only have it at the level of the energy levels. That was sort of an additional difficulty with respect to the renormalization procedure you put in place, in which you start from something that is like an infinite matrix, which has anyway, it has the right energy levels. And then you say, okay, let's compare these to some finite cutoff, and then let's start lowering. If you just go with your nose, you'll see this sort of like shift sort of coming out naturally. Like for instance, in your paper, you have it as one of the, at second order in perturbation theory, one of the corrections. In this case, it doesn't grow with lambda, so it's just a correction. It's one improvement, but it comes from a very similar source, which is some exponent alpha minus EI in the excited state, the Laplace transform of the excited state with respect to the ground state. So there's something that looks similar also in your analysis.
No, it's not similar. I refuse this comparison, because in our equation, we have a nonlinear equation for energies. But the correction terms that we have, they depend on the energies at the same value of the coupling. So in fact, we have some correction terms. We say in the right-hand side, we have, in the left-hand side, we have some energy that we need to compute. And then in the correction term, there's also energy. So it's a bit the same energy. So it's a bit inconvenient because it's a nonlinear equation for the energy. It's in two parts, but it's the same energy. We never have any equations which compare
No, I know.
exact energies to the free energies. We don't have such equations.
Yeah, I know. But it's sort of, I'm just saying that the bare energy appears once you turn this machinery at second order in perturbation theory as some of the corrections. I'm just saying that
would appear,
which is formally similar to the way it happens, except as you're pointing out, we're pushing it to say this is actually exact to all orders and it's actually correct. And the reason why we didn't do it, we didn't do the analysis you did is essentially this, that we don't know really how to start. So one way to start would be to restrict, say, put this epsilon cutoff that Kamran mentioned at some point, so that now we have a finite theory, which have energy levels which are finite in the continuum limit. And then from there, start integrating out in Hamiltonian truncation and try to swap the limits. Take this other regulator to 0, while keeping the Hamiltonian truncation regulator finite. So this could be a way to get what you want, but it's not, I mean, it was sort of beyond what we did.
But for example, would your truncation still work? Would your prescription still work if under you have a difference of the two terms, right? And then in the first term, you have this shift where you shift the cutoff by the free energy. Would your prescription still work if you shifted the cutoff not by the free energy, but by the actual energy that you're computing?
I think
which would get you a nonlinear equation.
Yeah, it would get you a nonlinear equation, but then since this works, at least, I mean, you see, this would introduce differences with respect to the prescription we're using at some order in perturbation theory. But we're pretty sure, say, from the free boson examples, that at least there, our prescription is correct.
To all orders.
Yeah, you can see it from the plot, for instance, and I think we also have checks at least to third order explicitly in perturbation theory. I don't know if fourth, but third order for sure. And I think that would be already one order in which your prescription would differ. So I think it's really a little more subtle than that. We have an argument you can look at in the paper, but I predict, I mean, that's sort of like a nice direction for research as well. So we try to justify this prescription using, I mean, bounding the large limit of some Laplace transform, but we had to put in extra assumptions there because this Laplace transform is Laplace transform of a difference, so it's not positive. So as you taught us, you cannot directly use Tauberian theorems. So there's some other route we took in order to understand why that is a good thing to do. But really the only intuitive, the only reason why this is somehow nice is that with exactly that prescription, you get the energy levels expressed in terms of differences of correlators that don't have the largest divergence. They're connected. So you kill the vacuum in that OP that Kamran showed at some point. If you do any other shift, you don't exactly kill the vacuum at all orders in perturbation theory. So in that sense, it looks nice. But that's the only sense in which it looks nice. It sort of cancels out a big chunk of say, I mean, in technical terms, of the small time non-analyticity. There's some divergence 1 over tau square in all of these correlators at small tau, and that's completely canceled out when you take, of course, the connected part by the prescription. But that's not, I know it's not what you're looking for, but it's somehow what we came up with.
No, but I mean, I hope your prescription is correct. I mean, you have a good evidence. I was hoping that perhaps one could use your results now to understand it better. Because what about, for example, in the usual Hamiltonian truncation, even in the flat space, there is in principle, we know that things will get complicated if the vacuum energy is divergent. Right.
Yeah, maybe I should let Kamran speak. Sorry.
Kamran. So as you know, there is if the perturbing operator has a large dimension, then the vacuum energy is going to become divergent. Right. So this is you could say it's a bit similar to what you have here. So again, the vacuum energy is going to diverge with the cutoff. And in that case, so some people try to still compute energy levels in spite of this divergence by doing this subtraction that you did. But as far as I remember, they, at least in some cases, they could get away with what you call naive subtraction, where you did not have to do the state-dependent subtraction. Right. Or maybe they even in that case they had to do state-dependent subtraction. Do you remember?
So that they have that one, that the one that I've seen is that has that naive subtraction. It doesn't have
naive subtraction.
But just one comment about the thing that you mentioned, that this shifted part is the energy of that point. So like it's not the energy of the free theory. I did that long back. If it's not any mistake I did in numerics, it was not converging to the correct value. So that's, I'm not 100% sure, as you know, like this numeric sometimes is not working because of some mistake in code, but but that's happened. Although that itself has some subtlety, that what is the energy of that part, maybe you should do some iterations, right? Like take that energy again back to it and then do that. Maybe in that case it works, I don't know, but that's not practical, to be honest. So that's just one comment about what you said, which makes it a nice prescription if it would have been the case, but yeah, I don't know if it works in practice.
About your question on like more general situations, again, what this prescription does is subtracting a disconnected piece. So one could hope that it would work in all cases in which these divergences only come from disconnected pieces, like what you're mentioning when the vacuum energy is divergent. That said, this is like, I mean, it's one direction. Like one would like to, we think it could be worth to at least check if it does work in one of these cases, or if it doesn't work, how this differs from ABS. But it's a very good point.
Thank you.
I have a question about the rate of convergence with lambda. So you say the power of lambda is related to the lowest dimension operator in the boundary spectrum, or in the lowest dimension energy in the Hilbert space. But in our computation, it was the first operator. It was sort of determined by a local operator in the bulk that appeared in the OPE of the deforming operator. Right? You took the deforming operator, you take its OPE, and then the first operator that appears there, that's what determines your
that's a good question, because here that when I'm talking, I was fast, I kind of like put all of the details on the rug. So here when you, I was talking about taking the epsilon to 0 and all of this tau is going to 0, you can have two source of singularities, right? Some of them are this V actually meet in the bulk, not at the boundary, which is the one that you're talking about. And some of that, there is the case that all of them are actually meeting at the boundary. And it turns out for this case, at least for our case in ADS, the main contribution of the singularity are actually from the one that all of them simultaneously go to the boundary, not the meeting at the bulk. So there can be, yeah. So that's probably, so there
saying that the other powers are subleading.
Yeah.
Mm-hmm.
Yeah.
But so at some point, if your perturbation is bad enough, then you get weird powers, I guess, related to bulk.
Sorry, can you repeat that?
If your perturbing operator is, or your perturbation is close enough to marginal, then you get extra powers there that are related to bulk operator dimensions.
Yeah. So here,
which probably require the same kind of renormalization that we introduced.
That's why I was started with this this part that we should be careful about that. The theories we consider has this condition.
Well, I'm talking about the bulk dimension. I'm not sure if that condition
right.
is
right. Okay. Right. Yeah, that's true. Yeah.
right? Because what you've been regularizing now are like the infrared divergences.
Yeah.
I'm talking about the case where the UV
Meaning 5.4
divergence or.
So in 5.4, what we, so for example, that's the case in 5.4, and we have like we normal order the theory, and then so that reproduce a phi squared term there. That's one thing that happens there. Yeah, we take care of those kind of UV divergences like that. Okay, I thought you mentioned this. Yeah, so there, that's another procedure that you should independently do. Yeah, it's not related.
Okay.
Or can I ask a very naive question? It's the one I already asked once, but I'm still confused by this. So if I have ADS, which is huge, I get flat space, and then isn't there an infinite series of corrections in one over radius, and the small radius limit in particular, it should be very much dependent on how I decide to put my theory in ADS. It should not be universal at all or anything like that. But you are doing plots that go all the way to r equals 0. I'm totally confused by I mean, in the free theory, maybe I understand. Probably there it's easy to pick one, but in these E8 theories and Sine-Gordon and these more complicated theories, aren't there infinitely many ways of propagating things inside? Why can't I add in your case phi 6 over some times some curvature, for example, here?
So in principle you can, but this is the one that we're studying, right? That's true.
Okay. Okay. No, because I'm thinking from a point of view, if I have a theory that I know how to study, but not from a Lagrangian point of view, like Sine-Gordon or the strongly coupled interval
but phi
theory.
6 has exactly the same dimension of phi to the 4. So if you add phi 6, we are in 2 dimensions. So phi 6 is not going to be, it's going to modify the short, if you add phi 6, it's going to modify the theory at short distances.
Exactly. That's what I'm saying. So at short distances.
But we are assuming that at short distances, it's the same as they usually be the same as in flat space. So we cannot add phi 6. That will already modify the theory at short distances.
Yeah, I'm not sure.
Well, no, with 1 over radius of ADS.
Why 1 over radius? Phi 6 has exactly the same dimension as phi to the 4th.
2D, they are all, yeah.
They all have dimension 0, right? So
Yeah,
they
all have, so there's no 1 over radius.
Oh, but I can put m square or 1 over radius, right? M square and 1 over radius square have the same dimension, no?
But the question is, can you add phi to the 6 or not? I think there's a very good reason not to add phi to the 6, and it's justifiable on the grounds that at short distances the theory should be exactly phi to the 4th.
Well, let's say, for example, Sine-Gordon. Sine-Gordon, you have all the terms, right? So you have an infinite series.
Mm-hmm.
So now what would it mean to put the theory in ADS? What should I do? I mean, a priori, I could imagine.
No, but Peter, would you like to add relevant operators or irrelevant operators? I understand. Irrelevant are also not allowed to add.
That's probably what I'm confused about. So let me see. So in this language of Sine-Gordon, how do I think? So all these operators are have dimension 0. It's an infinite series, right?
Yes.
Yeah, I mean, I think
then you can pick the cosine to have a relevant dimension. Positive greater than 0, but less than 2.
Yeah, so our perspective here is that we start from some, let's discuss this case in which we have a fixed point in the UV, and then we add some relevant deformation. Now this procedure identifies your theory. As Slava says, if you add the different relevant deformations, then you have another theory, which will have another flow. But here in Hamiltonian truncation, we're just fixing from the onset what we want. And then it's the same as Slava is saying, because the large radius of ADS is short distances in the bulk is the same thing, right? It's just the same as what we want to get at the end. And that's fixed once you have a relevant deformation, then you just flow. So in all of these cases, we just fixed our Hamiltonian, and in the case for the conformal boundary for a conformal field theory, we also have some additional constraint. Well, in all the cases, you have one additional constraint to UV, which is what boundary condition you want to put, but that's normally a discrete set. Like for instance, in the cases we know, into D at least, there is a discrete set of choices that doesn't break the isometries of ADS. Once you fix the boundary conditions and what relevant deformations you want, then it's just an RG flow. So there's no ambiguity anymore. But what you're saying is that we could consider more RG flows, which travel in a larger coupling space, which is definitely true.
Okay, thank you. Yeah, I was confused by that. Yes, that's good.
Anything else? Okay, if not, we can thank our speaker again. See you next week.